The human brain is not a blank slate. It is a structured information processing system forged entirely by the pressures of biological evolution and natural selection. Cognitive load theory derives its entire mechanical framework from this biological reality. The theory divides human cognition into two categories. First is biologically primary knowledge. As illustrated on the left, this includes native language and facial recognition, information we evolved to acquire automatically. Then there is biologically secondary knowledge. This encompasses complex cultural developments like algebra, biochemistry, and written language. Our brains did not evolve to acquire these naturalistically. They require conscious, deliberate effort. Educational institutions exist almost exclusively to transmit this secondary knowledge. When educational models fail to recognize this biological divide, they attempt to teach secondary knowledge using the unstructured, naturalistic processes reserved for primary knowledge. Effective instruction requires engineering methods that actively bypass our evolutionary limitations. We must design systems to teach information we were never biologically wired to process. This schematic maps the two primary structures of human cognitive architecture: working memory, represented as a narrow conduit, feeding into the massive neural network of long-term memory. Working memory is our conscious processor. We rely on it to handle novel, biologically secondary information, but its capacity to hold and manipulate data is severely restricted. Long-term memory is the final destination. It operates as a virtually infinite database, where information is stored in organized blocks known as schemas. The primary threat to the working memory bottleneck is a variable called element interactivity. Element interactivity is not a measure of the total volume of information. It measures the degree to which distinct elements must be processed simultaneously in order to understand a single concept. When complex, highly interdependent concepts attempt to move through the narrow conduit of working memory, the elements jam. The conscious processor is overwhelmed, and the system halts. The core engineering problem of instruction is finding a way to push high-element interactivity information through a rigid biological bottleneck without crashing the system. Looking at the working memory bottleneck, we divide element interactivity into three types of cognitive load: intrinsic, extrinsic, and germane, constrained by a hard capacity limit. Intrinsic load represents the material's inherent complexity. It is essential and cannot be removed without altering the curriculum. Extrinsic load is cognitive friction. It's generated by poor instructional design, confusing formats, and irrelevant details. The brain processes intrinsic and extraneous load identically. Both draw blindly from the exact same finite pool of processing power. Germane load is the actual mental labor of forming schemas and successfully transferring that organized knowledge into long-term memory. Because of the strict capacity limit, germane load relies entirely on spare processing power. If intrinsic and extraneous load consume the available space, germane processing is compressed to zero. If a curriculum features high intrinsic complexity, any poorly designed extraneous instruction will completely eradicate germane processing, making learning biologically impossible. Modern instructional theory often prioritizes teaching broad, general cognitive strategies and inquiry-based problem-solving over domain-specific content. Cognitive load theory identifies a mechanical flaw in this approach. General problem-solving strategies are biologically primary. Normal human beings acquire these strategies automatically and unconsciously at a very young age, entirely without explicit instruction. When learners struggle in complex, unfamiliar domains, they are not lacking a general problem-solving strategy. They are lacking specific knowledge. During unstructured inquiry learning, a student defaults to a primary strategy called means-ends analysis. This forces them to blindly generate and test random solutions in order to bridge the gap between their current state and the goal. Holding multiple potential variables in mind while testing them creates a massive spike in extraneous element interactivity. Working memory is immediately overwhelmed by the search process. Unstructured inquiry weaponizes extraneous load against the learner, occupying the exact working memory capacity required to acquire the specific schemas they actually need. Cognitive load theory rejects multivariable classroom comparisons, such as weighing a chaotic inquiry lesson against a structured lecture, as scientifically meaningless. The theory derives its principles exclusively from single-variable randomized controlled trials, isolating exact cognitive mechanisms. One foundational trial visualizes this. On the left, the control condition tests conventional problem-solving. On the right, the experimental tests a worked example. In the control, actively attempting to solve a novel problem using means-ends analysis maxes out available capacity with extraneous load. In the experimental condition, the learner studies a problem of identical complexity, but the steps are explicitly solved for them. By removing the need for a random search, extraneous load drops, and germane processing pushes a completed schema into long-term memory. Providing the completed steps eliminates the cognitive friction of searching for an answer, which frees up capacity to memorize the structural components of the problem itself. The worked example effect demonstrates that to successfully upload schemas into long-term memory, instruction must proactively bypass unstructured problem-solving. We can now observe how the cognitive architecture operates after successful learning has occurred, and schemas are permanently stored. According to the environmental organizing and linking principle, when an individual encounters a familiar problem, stored schemas flow backward from long-term memory into working memory, serving as structural scaffolding. This backward flow effectively circumvents the initial biological limits of working memory. Information that once possessed high-element interactivity is repackaged and processed as a single consolidated element. This structural shift creates a direct downstream consequence known as the expertise reversal effect. Highly explicit instructional guidance that is optimal for a novice will actively hinder a learner who has achieved expertise. For the expert, redundant guidance forces them to cross-reference their pre-existing schemas with the unnecessary external instruction. This generates an artificial spike in extraneous load. This unified system architecture precisely predicts several other validated phenomena, including the split attention and transient information effects. Instructional design is a strict engineering discipline. Developing educational models without mapping them directly to the evolutionary constraints of human memory ensures systemic failure.